Have you ever stopped to think about what's really going on inside a simple wire? I mean, from the outside, it looks totally still, right? But it's actually this hidden world of, well, of chaotic energy. Okay, let's dive right in and explore this fundamental force that pretty much powers all our electronics: resistance.
So to really get a handle on our modern world, we've got to think small. I mean, microscopically small. So forget the plastic cover, forget the solid copper you can see. We're going to shrink ourselves way, way down to the atomic level to see where the real action is.
And here it is, our subject. A plain old copper wire. Looks pretty basic, doesn't it? But really, this is like a super highway for the energy that runs our lives. And just like any highway, it's got its own speed limits and, as we're about to find out, its own traffic jams.
All right, so before we even think about connecting a battery or anything, the inside of this wire is, well, it's anything but calm. It's this constant, chaotic ballet of particles, a dance fueled by pure energy.
You see, inside this wire, there are tons of these free electrons just bouncing around, not really attached to any one atom. They're fueled by heat, and they're just zipping and ricocheting off each other like crazy. But here's the key. All this movement is completely random, totally disorganized. So with no overall direction, there's no electric current. Not yet, anyway.
And this is the moment everything changes. We hook up a voltage source, like a battery. Now, it doesn't just shove electrons along. What it really does is create a new condition inside the wire, an electric field that basically sets up a gentle, consistent slope from one end to the other.
And with this new slope in place, that random dance of electrons suddenly gets a bit of a purpose. I mean, they're still moving around erratically, but now they have a general drift in one direction. And this organized drift, this big collective movement of charge, that is what we call electric current.
So the electrons are finally flowing, right? But is it a smooth ride? Is it a wide-open highway? Not even close. The very material of the wire itself creates this natural, unavoidable obstacle course. Now check out the path of this electron. It's not a straight line, is it? An electron gets going, it accelerates, and then bam! It slams into a copper atom, loses some energy, and gets knocked off course. It speeds up again, only to collide again. And this isn't a rare thing. It's happening a mind-boggling number of times. We're talking trillions of times every single second.
And this phenomenon, this constant crashing and bumping, that is the very essence of electrical resistance. It's not something we add to the wire. It's a fundamental property of the material itself. It's the microscopic traffic jam, the physical opposition that's happening because of all these collisions.
You know, an easy way to think about this is like water in a pipe. Voltage is the water pressure, pushing everything through. Current is how much water is actually flowing. So what's resistance? Well, that's how narrow the pipe is. Sure, high pressure will get you more flow, but if you have a really narrow pipe that's high resistance, it's going to restrict that flow no matter how hard you push.
Okay, so we've got this idea of a barrier, but, science isn't happy with just ideas. It needs to measure things, to predict them. So let's see how this physical reality gets captured in one of the most important laws in all of electronics.
And here it is. This simple, beautiful equation is Ohm's law. It perfectly describes the relationship we've been talking about. Resistance, which is R, is just the ratio of the voltage, V, that you're applying, to the current, I, that actually makes it through. It's such a direct way to put a number on exactly how much a material resists electricity.
So what does this mean in the real world? Well, it's pretty straightforward. If something has high resistance, you have to apply a lot of voltage, a lot of push, just to get a tiny little trickle of current. But with low resistance, even a little bit of voltage can unleash a huge flood of current. And that difference is absolutely crucial when you're designing any kind of electronic circuit.
So far, we've kind of been talking about resistance like it's a problem, this natural obstacle we have to deal with. But this is where things get really cool. This is where human ingenuity just flips the script. What if we could take this barrier and turn it into a precision tool?
So let's think about a real-world problem. You've got a little LED light and a powerful battery. If you just connect them directly, poof, a massive current flows right through and the LED is toast, instantly. So how do we stop that from happening? We solve it by intentionally adding resistance. This brilliant little component here is a resistor. It's engineered to provide a very specific, known amount of opposition. It doesn't stop the current, it just controls it. It's basically telling the electrons, okay, you can move, but not too fast, and that limits the flow to a safe level for the LED.
And this amazing little tool has evolved right along with our technology. For decades, we used these through-hole resistors. You know, the little cylinders with the colored stripes that told you their value? But as our gadgets got smaller and smaller, going from bulky radios to the smartphones in our pockets, the parts had to shrink too. And that gave us these tiny surface mount or SMD resistors. The shape has changed, but the job, control, is exactly the same.
A fixed resistor is great for setting one specific current. But what if we want to change that control on the fly? What if we want to put the user in direct command of the circuit?
Well, that's the magic of a variable resistor, which you might know as a potentiometer. Just picture a long strip of resistive material. There's a little contact called a wiper that slides along it. When you turn a knob, like a volume control or a light dimmer, you're changing how far the current has to travel through that resistive stuff. A shorter path means less resistance and more flow. A longer path means more resistance and less flow. It's that simple and it's that powerful. And this is where it gets really clever, because we can even tailor how that control feels. For something like a motor, you probably want a linear change. You turn the knob halfway, you get half the speed. Simple. But our ears? They hear volume logarithmically. A linear volume knob would feel all wrong. It'd feel like all the sound jumps up at the very beginning. So for audio, engineers use logarithmic potentiometers that actually match our hearing, which is why turning up the volume feels so smooth and natural.
So let's just pull it all together, the whole story. You've got the battery, which provides the push. That's the voltage. You've got the electrons that respond to that push by moving. That's the current. The atoms of the wire itself create that natural obstacle course. That's resistance. And finally, the resistor is our purpose-built tool, our precision-made obstacle that we put in to master that flow. See? It's all one connected story. So in the end, it turns out resistance is so much more than just a flaw or some kind of inefficiency. It's the fundamental principle of control in electronics. From the glowing filament in an old light bulb to the volume knob on your stereo, it's the deliberate use of this atomic-level traffic jam that makes all of our technology work. So the real question is, what will you control with it?